Hey, how's everyone doing today? Cassandra and Nick, good to see you here. We're going to get going. It is time. What should we do? What should we do? We can start off with some analytics or start off with some assignments. Chapter 5 is coming up right here. I'm going to send out some big announcements. PepsiCo event tonight. So grab that video, but put what you want to do in the chat. Got an email I had to reply to there at the very start. Oh, so you're out here. PepsiCo Analytics at 7 p.m. tonight. I'm going to send an email to everybody. PepsiCo event, 7 p.m. tonight. Send this out. Announcements. What questions do people have in the chat? Chapter 5, yeah, homework. Let's do that. Let's do the homework. It's the first homework, right? I'm going to send this out right here real quick. PepsiCo event tonight at 7 p.m. Tonight, I will have DK graduate speaking about PepsiCo. Here. Okay. Boom. There we go. 7 p.m. Sending that, and then we'll start here in one moment. PepsiCo event tonight. PepsiCo event tonight. There we go. And PepsiCo event tonight. There we go. Okay. Hey, what's up, Savannah? Canvas content. Hey, what's up, Andrew? Good to see you here. Let's throw some points. Let's do the chapter 5 homework and we do some Canvas content. Yeah. Ma Pearson. How are people doing today? How are people doing in the chat? We're getting the Ma Pearson going. We'll do some Canvas content after this. I need to get the thing in the video right here. I need to get the timestamps. There I am live on YouTube. There I am talking to myself. Terrible? What's wrong, Nick? Why terrible? What's up, man? What's happening? Why terrible? I'm sorry. What's terrible? Thank you for sharing. I hope you're doing all right there. What's terrible? If you want to share, that is. So, oh, I didn't even know who won the Super Bowl. Hey, Kat, good to see you there. Oh, I'm so sorry. Well, I didn't mean to laugh. I was really worried. You got me. Well, I mean, I'm sorry. My cousin's a Buffalo Bills fan, and they've been like losing for forever. I don't know. When was the last time the Bills won a Super Bowl? We're gonna do some chapter 5 to start. Chapter 5 homework. I'm a Patriots fan. They lost Tom Brady, so no more Tom Brady, no more Super Bowls. That can't be the homework. No way is that the homework. No way does chapter 5 homework have that much. Okay, I clicked the quiz. Okay, number 5 on chapter 5 homework. Okay, let's start this up right here. Number 5. So we're starting right here at 10, 13, Stat 201, chapter 5. Homework, question 5. Or was it 6? Number 6. Here we go. Number 6. Let's do it. Here we go. Okay, number 6, part D. Yeah, let's take a look at it. Okay, so this is going to use the normal model right here. So what are the important numbers we need to know? Drop them in the chat, and then let's talk about what they mean. What are the important numbers we need to know for the normal model? And we're going to bring up the apps right here. So let's bring up the apps. It's going to help us out with this. This does use the empirical rule, and they make sure on the test, or we make sure on the test, that you know to use the empirical rule right here. And what does the empirical rule mean? Well, let's take a look at it. I thank you to Adam Spanbauer for creating these apps right here. So this is what the empirical rule means. We're going to go over here and go to the normal model. I should have maybe linked to that one, the normal model right there. 68, 95, 99.7. Sounds a great job right there. So what this means is if you go between, let's look at this right here, between -1 and 1 you will get 68% of the area. And it's almost exact. Like, we could round this to like 1 decimal. Let's do this. Oh, there we go. Z-score of 1. You see a Z-score of 1 plus or minus 1 Z-score, 68%. If you go to 95, you get to a Z-score of 2. And then 99.7, you get to a Z-score of 3. So as you go to further Z-scores, more areas containing the curve. Does that make sense right here? I think maybe the visuals can help. Like, this is the percent of area contained within a Z-score of 0.5. And as you go to 68% of the area on the curve, like look at more area being contained, then you're going to see you're at a Z-score of 1. Now, that's 68 right there. Now, we could go to more decimal place exactness. We just say 68, 95, 99.7. But it rounds to basically 1 Z-score, 2 Z-score, 3 Z-scores. And Z-scores are how many standard deviations you're going out on the curve. So that's 1 standard deviation. Now, we can change the mean to something like 70, the standard deviation to 5. And now if you look at the curve on the bottom, it has a mean of 70, and the standard deviations are 5 going out each time. So that's 1 standard deviation, even though it doesn't have it marked. 1 standard deviation, 2 standard deviations, 3 standard deviations, 4 standard deviations, because the standard deviation is 5. So very important to understand that the normal is the shape of the curve, the mean is the center of the curve, and the spread is the standard deviation. So shape, center, spread is what we're talking about. So here we are with the question. It says it has a mean of 100. What's wrong with A? Graphic A, what's wrong with graphic A right here? And so we'll do part D here in a moment, Cassandra, and this is good help for anyone else working along with this. What's wrong with part A right there? The wrong mean, you got to, Cassandra, get those points. And then we look here at the next ones. This does not go 68 in the middle. It should be 68 in the middle, so this is the right answer. Now, this is going to be useful for solving the rest of the question, but here's the thing. You should be able to draw all this. I know that sounds crazy right there, but I'm going to bring up a Word document, and it says a mean of 100 and a standard deviation of 18. So what you want to be able to do, rather than use their work, is draw it out yourself. So you go over here, and you say it's normally distributed with a mean of 100 and a standard deviation of 18. So whenever you draw this out, I always suggest putting the mean at the center, and then going down 1 standard deviation, 2 standard deviations, 3 standard deviation. What do we call this curve that just has the Z-scores on it? It's called the something curve. So this curve right here is called the what normal curve, because it's got all the standards on it. It's got Z-scores. Everything on this curve right now is Z-scores, because those are just the Z-scores. We call it the what normal curve. So I suggest drawing this first. It's called the standard normal curve, the standard. So that's the standard normal curve because everything's standardized on it. And then below it, I'm going to put 182 because that's a difference of 18 right there. We're just going down by this difference each time. And the mean is at the center of the curve. So we'll highlight the mean here at the center. And the mean goes right there. And then the differences are down by 18 each time. And then we go here and do 74. And then we go here and do 66. We go up and do 118. And we go to 136 and 152. And that's 3 standard deviations above the mean. Now we can also do other things, but I'm going to kind of hold off a little bit because how much percent of areas between here and here cast? Well, I just gave the answer. 68% is within Z-scores of -1, +1. And that's what we were just talking about with the empirical rule. So this drawing, which they give you, is going to be the key to solving the questions. So let's look at their questions, which we have a drawing, but I do suggest drawing it and practicing it. 99.7. So we need to go up and down how many Z-scores right now. 99.7. You need to go plus or minus how many Z-scores. Do your own drawing and then practice and know how to solve the answers. 3, you got it. So do you see the answer? This one's really, well, I mean, if you know how to do it, it's really easy. The Z-scores are plus or minus 3. Great job, Skylar, right there. Excellent work, too. Plus or minus 3, so 66 to 152. And you can check your numbers up here. Ooh, what have I done? Look at this, Brian can't math. Uh-oh, you see, that's where we got to be. Oh, look, right here. Brian can't math. Check your work. And this should have been 64. And that should be now 44. Oops, we're doing that in green. So, yeah, you'll make errors every once in a while, but there we go, 44 and 152, because in plus or minus 3 standard deviations is 99.7. Megan, good to see you here. Another 50 points for Megan. So be careful. We all make errors right there, but you can use their work to check your work. And we see 46. And really, I can't math today. What is up with me? Yeah, I really can't math. Wow.
Wow.
46 and 152. And once again, use their numbers to check yours. 46 and 154. Why can I not math? I need to slow down. Math is hard. Use their work to check your work. Make sure you're adding right here. I added wrong right there. That looks like I added 16 to it. There we go. And so now the numbers are correct and follow the curve. So let's look at the next question right here, which says, what percent of IQs are higher than 154? Now, this is a tougher one. 154, you can see it over here. We just said 99.7 is inside of here. So what, great job, Cassidy. Yeah, you're on fire right there. So what Cassidy did they found 0.3 on the outside and divided it in half. And if you trace across this, you will get just this, you'll get 100%. But you want to make sure you're doing the inside-outside trick where 99.7 is inside, 0.3 is outside, and then do the remaining percents on the outside. The more you can draw this curve and solve for the answers, the better you'll do. And so that's just the upper top above 3 standard deviations right there. And so let's put the answer in there. Great answer right there. Go to work. We're almost to part D. I think is this it? Here it is. What percent should be between 82 and 100? Abigail, good to see you here. So now 82 and 100 are between a z-score of what and what? 82 and 100 are between a z-score of what and what? So there we go. We got our drawing on the screen. 0 and -1. So how do you think, if we know that this is 68% here, what do you think that is? So, Cassidy, you might see it now with the drawing. So look at the symmetry of it. And if that whole thing, that green thing, you did it. That's it. Perfect answer. Great job. There you go. The drawings can really help when you do the drawing of it. It's like, okay, I see it now. It's half of 68. Now this says above 136. So let's go back to our drawing. And usually you want to find something that goes right up to it. So you go to 136, and we know this is 95% of the area. Does anyone know the answer to this one yet? Yeah, and then use the empirical rule numbers. Use the empirical rule numbers. Don't use the calculators on these ones. This uses just the empirical rule, and the test will tell you that. 2.5. Skylar, great job. What Skylar did right here is Skylar said 5% is outside, and then cut that in half because this is symmetry on the outside, and you just want this area over here, which is 2.5. So 95% within -2 or +2, and that's how knowing the empirical rule can really help. And there are questions just like this on the test. This is a really great question to see if you know how to do it. Make sure you check above, below, but that's an amazing question. A z-score has a mean of 0 and a standard deviation of 1. Z-scores are standardized all data sets. Yep, 2 of those are true, so they're all true. I probably know all those facts, but I just read the first 2. Like, they have a mean of 0 and a standard deviation of 1. Yep. They standardize data sets. Yeah, that's why we use them. So a z-score is a measure of how extreme. Yep, we can see how far something is away. A z-score tells us how many standard deviations. That is literally the definition of a z-score. You got it. Nice job, Cassidy. And I just checked 2 of these. It's like if 2 are true, then you can't select 2. You have to say all of the above. So really good question right there. And know those about z-scores. Like I would know each of these. Like z-scores have a mean of 0 and standard deviation of 1. These are z-scores. I labeled them over here. Z-scores standardize a data set. That's literally what's going on here. I talk about somebody with an IQ of +1. Z-scores measure how extreme something is. Yeah, we could find out the extremes based on a z-score. And last but not least, a z-score tells us how many standard deviations a value is from the mean. Be right back here in 2 seconds. One moment. We are coming back right here. So it's time for some Canvas content number 2. Thank you, everybody. The fun of working from home. You get a contact appointment call and you're like, hey, it's my contact appointment. For those who have seen, Brian has been struggling with his eyes all semester. So happy that my contact appointment finally is starting up here. And maybe I'll be able to see more clearly. That'd be amazing. We'd love that. What's funny is today I'm actually seeing pretty well. So it's like, oh, maybe I'll be able to see really well. And then it's like, okay, wait, I can already. Today is a good day for vision. But yeah, so I'm glad they called and we got that appointment made. How about some Canvas content number 2? Who's ready for some Canvas content number 2? And put all those questions you have in the chat, because we don't have any questions after this. We could do more chapter 5. And great job, Cassidy, working on that early. It's due when? Later this week, right? Chapter 5 is a tough one. So Stat 201, Canvas content number 2. Let's go do this. Canvas content number 2 coming right up. Okay, it's time. Oh, wrong button. Let's get in preview Canvas content number 2. Outliers of a box plot are blank IQRs above and below the mean. So how far away are outliers in a box plot? How far away are they? I'm going to ask you some more questions about box plots here in a second. 1.5, great job. And that's a number I'd memorize. So let's take a look at them. Remember, we don't just solve these questions. We talk about, some really cool advanced things we can do, and we make sure we understand the concepts. Great job, Skylar, right there. So here we are. I'm going to show you a few things, not with that one. This is using R to do data analytics. Let me go to ggpub R on this. Okay. So I want you to think, which of these variables could I do a box plot with? And just look at the names if you want. Which of those variables on the screen could I do a box plot with? So think about when we use box plots. This is the important learning thing. When do we use box plots? And then think about which of these. You don't have to look at all this. You can just look at this right here. Which of those variables could I make a box plot with? So which of those variables could I make a box plot with? What do you think? Thoughts on that? So box plots need to be what? GPA. Great job, Megan. Yes, GPA. So we might be able to use this sometime. Let me see here. Y equals GPA. I'm going to do it. Look at that. Boom. Box plot. And then what happens when I do this right here? Take a look at this. That's a box plot. And then what do we get right here if I do this and put gender right here? What do you notice we have now? This was just GPA, which is just the GPA variable. And then now what do we have here? This is a box plot. What is this graphic called? Side-by-side box plots. And that's when you add a categorical X. Do you see down here, we were doing box plots with a quantitative Y, and you're still using a quantitative Y down here, but we now have what are called side-by-side box plots. And this is why I love coding in R, because I should be able to go right here and just add in one more argument and go to color right here. There we go. Look at that. Nice. Or we could go to fill. And there you go. So we made a really nice graphic right there pretty quickly. But so if you want to learn how to code in R, let me know. But we can see where the outliers are. Now you have to be careful. What do you not ever see in box plots? What's one thing you don't see when someone makes box plots for you? Like, what do you not see right around here-ish? What do you not see? You don't see the fences. Skylar, you're on fire right here. You don't see the fences. This is the lowest point that is not an outlier. That is the minimum. So they both have similar ranges, kind of similar, but you don't see those fences. The fences are just a graphical technique, and this should be notes 3 right here. No, it's notes 4, is it not? It's over here on notes 4. You don't see the fences. We remove the fences afterwards, so they're just a graphical technique. Sometimes they're, like, if there's this little gap in the data, then the fence has to be in there. The fence is 1.5 IQRs above and 1.5 IQRs below. Sometimes I like showing this here by literally taking that IQR right here, and you can see literally if you do a IQR and then do another 1.5 IQRs right there, that's 1.5 IQRs, that's where the fence is. So literally going up the length of the IQR 1.5 times and down, but this one's negative. There's the mathematics for where outliers begin, and graphical software will always draw this stuff for you. So We have box plots and side-by-side box plots. Really great way to display quantitative Y variables. Abigail, good to see you here. I got both Abigails here. Box plots. Ooh, look at this. Careful. Box plots are not ideal for comparing multiple groups. True or false? Box plots are not ideal. And this is a plural. True or false? A lot of people get tricked. That is correct, Skylar. And take a look over here. Am I comparing multiple groups over here? So is Brian comparing multiple groups right here, the GPAs of multiple groups? Am I comparing the GPAs of multiple groups right there? I could change this to handedness. Yes. So can you use box plots to compare multiple groups? There's the GPA of people by their handedness and probably just less data right there. So very clearly you can use box plots to compare multiple groups. And be careful, it doesn't say a box plot. It's talking plural right here. So that is false. Below is a contingency table. Now, a contingency table displays what kind of data for us? So you've got your hint on the screen. It's paired with a mosaic plot quite often. A contingency table displays what kind of data for us? Categorical is correct, Skylar. Go a little further. And it is categorical. Categorical what, though? Categorical what? A contingency table is what kind of categorical data? And the reason being, it's not just a categorical this, it's a categorical this. I'm blocking it right here. Bivariate, which means you're doing 2 data points. So to review, what is this called right here? This is called a what? Think of something F table. This is called a... What is that called right there? That's called a what table. Because it's just how often things occur. So you could call that a what table. Hints are on the screen. Look at the top right corner. So that's just one variable, a frequency table. So that's a frequency table. So you're seeing a frequency table right there. But watch this. What do you notice? You don't have to know all the code I'm doing, but I'm adding a second variable right here. A second categorical variable, and now you get a contingency table. So this is a frequency table right here because it just shows one variable. And then this is a contingency table because you can see the bivariate combination of gender and handedness. So a frequency table is one categorical variable, and a contingency table is one variable, like handedness, contingent on gender, depending on which way you want to talk about the X and the Y. Now notice these are not 2 categorical variables over here. That makes a different graphic. That's side-by-side box plots. If we wanted, we could turn this into a mosaic plot. And I guess I'll show that really quick because I've got access to a really good one. I think okay, so 2 seconds. I like showing kind of the neat stuff we can do right here. Let me go grab that code because I literally think I can just copy paste my code that I already have for this. Because I was doing examples with this. So here you go. There is a mosaic plot. There's the mosaic plots. And what do you see inside the mosaic plots right here? Let's show the contingency table again. What do you see inside the mosaic plot? Inside the mosaic plot, think about those percentages right there. What do you see? Very important question. Like 86.9% of males were right-handed. 9.58% of males were left-handed. So what do you see inside of there? And so if we go to the males, there were that many males. And we have 11 out of that, so 3.51%. What do you see? What would these be called? Like 86.9% of males were right-handed. What is that called? Of the males, 86.9 were right-handed. So given someone was male, we call this the what distribution. Keywords you should know. Starts with a C. The what distribution. So you would say, okay, for only males, so you'd add up all the males, which is where we're going with this question. Okay, so we have all the males right there. 272 of them were right-handed, and that's 86.9. Kind of good answer right there, Skylar, called conditional. The conditional distribution is when we talk about one group right here. So this is called the conditional distribution. And conditional distribution is right here, where you say you set a condition for one variable and look at the other. The marginals are on the outside, which are on the outside of the mosaic plot. Like there were more people dead on the Titanic than there were alive, and more third and crew. You can see the margins right here, which is also the margins of the table. When you look at a contingency table, the margins on the outside here. So make sure to understand those words, and you can see right here there were more females than males because this is the margins of this contingency table, of this mosaic plot, excuse me. But key things to know, and just seeing graphics and understanding them is part of the process of learning how to do the analysis. So what do you notice right here? It says, what percent were neutral? So is that a marginal or conditional distribution? So put an M or C in the chat. It says, what percent were neutral? And then we're going to highlight what we're talking about. But is this marginal or conditional? What percent were neutral? Which one? So is it considering one or two variables? So marginal only considers one. Marginal only looks at one variable. Conditional looks at two by looking within the levels. I am popular today. So this is going to be marginal. And great answers right there. It's marginal, and let's show why. You ready? It says what percent were neutral, right? So to figure out what percent were neutral, what two numbers are we looking at? We would be looking at the total neutral out of the total. And do you see how this is a margin of the table? So that's a margin over there. All this other information doesn't really matter.
It doesn't matter.
And great job, Scholar, right there. So that's a marginal distribution, 229 out of 992. And once again, we're trying to make sure we understand all the concepts right here because you never know what you might see on the test. So know the words marginal and conditional and know how they apply. It says round to a percent. So we're going to have to take this and put it to 0.08 right there. So now it says, what is the probability of a student born in Tennessee being an honor student? Is this considering one or two variables? It says, what is the probability of a student who is born in Tennessee being an honor student? Is that one or two variables? So good steps to see that we understand how to do it. Is that one or it's two variables, right? So that means it's probably a what. I mean, it is this, but it sounds like we're talking about a what distribution right now. Sounds like this is a what distribution. Well, so this is a bivariate graphic. Good answers, Nick, right here. And so is this conditional or marginal? Conditional means we take one variable and look within it at the distribution of the other. Like in this graphic over here, what is the probability of a male being right-handed? So it's not the probability of someone being right-handed, which would just be the total right-handedness out of all the data. But so does this sound conditional or marginal? Put a C or M in the chat. Conditional or marginal? Sounds conditional. Great job, Savannah, right there. So let's go and take this right here. And we are looking at what is the probability of a student born in Tennessee, so born in TN, being an honor student. What is the math? See if you can solve the mathematics right here. What would we solve right here? What is the answer to the question mathematically? Like, show me the division we need. Yep, Nick, you got it. Yep, because now we have the, I guess maybe I should have done it this way, where I under or circle this right here, and then we would have born in being an honor student right there. So that's out of the total 50 out of 574. They're born in Tennessee, and they're not both of those. Excuse me. What is the probability of someone being born in Tennessee? What is the probability of someone born in Tennessee being an honor student? How would you have the question asked? What is the probability of a student being born in Tennessee? So is that conditional or marginal? Here, I'm going to solve this one real quick, and then we'll show that one. Is that conditional or marginal? If we say, what's the probability of someone born in Tennessee? I think you're right, Savannah, because does that sound conditional or marginal? And then it wants it to 3 decimals like that, it looks like. Is that conditional or marginal? So we're only asking one question right there, right? What is the probability of someone being born in Tennessee? So if it says, what's the probability of someone being born in Tennessee? It's going to be marginal. Good answers, good practice, everyone, to see how the other information doesn't matter, because you're only looking at this information right here. That's the margin of the table, where it only considers one variable. So the marginal distribution only looks at one variable, and thus we would be going right here, born in Tennessee, out of the total, And that's how we would do it. And that's the margin of the table, which only looks at one variable. It's not looking at within one level of a variable at another. That's just a margin. What's the probability of soon being born in Tennessee? Well, there we go. Look at that. And we'll do another version of this and talk over the concepts. There's the probability, and we've done it. There it is. We just talked about that one a second ago. We rounded right. Sometimes you round wrong. Okay, so here's another version of it. Let's take a look. If you analyze data with outliers, what should you do? If you analyze data with outliers, what should you do? Don't look at the answers. Just think about it. What do we oftentimes do with outliers? We give them what? So don't look at the answers, because then you're just, I don't suppose you're directing me off stars you ever data last 3? Yeah, I think, did we do that one yet? Is it the mosaic? We might not have done that yet, Doc. Good to see you here, Doc. I don't know if we've done that one yet. Have we? Let me, while people tell me what we do with outliers, I'll see if we have. We might need to do that next, because I don't think there's any questions next. I'm just going to yawn a lot. This one's due Wednesday, so I don't think we have. No, here it is. I got it. We have done it. Okay. Yep. Here you go, Doc. Thank you so much, Skylar. Yep. I put the links in our videos now, or in my assignments, so people can find it. What do we do with outliers? What do we do with outliers? Anyone know what we do with outliers? Don't look at the answers. This is a review of the notes. What do we do with outliers? It's at the very end of chapter 4. How do we handle outliers? Let me leave those notes right there. How do we handle outliers? What do we do with them? You could. Outliers and good answers, Megan, right there. Good practice. They always require special attention. You don't just, you might exclude them. You might not. They always require your special attention. So when it comes to outliers, you don't just exclude them. Maybe they're due to errors in the way people heard the question. Maybe, people lied, cheated. There's so many ways outliers can occur. We usually analyze the data with or without them. If they're a lie, we could remove them. If they're errors, we could fix them. But you never, ever ignore them. So if you look at some of these answers right here, I think some of them, the wrong answers, never analyze data with outliers. Well, if you look at the notes, as the notes say right here, so if you can't justify removing them, you can do analysis with and without them. So that eliminates that answer right there, because you can analyze data with outliers. Exclude the outliers, but justify why. That is very possible. Exclude the outliers without attempting to understand. That just doesn't sound like good statistics. Ignore the outliers. No, that's the complete opposite of special attention. So where we say outliers require special attention, ignoring them is the complete opposite of giving them special attention. So, and without attempting to understand them, we always try to understand the variation outliers. So exclude the outliers, but discuss why you felt justified. Also, you might not exclude them. That's another possible answer, but maybe this should say, what is the best way below to handle outliers? There is sometimes a good reason to remove outliers, true or false? There is sometimes a good reason to remove outliers. I gave a very specific example during lecture. There is sometimes a good reason to remove outliers. Well, so Nick, yes and no. We don't remove outliers because we don't like them. The number one reason to remove outliers is because the data is a lie. If somebody tells you that they drink 10 days a week, which was my example during class, so we don't usually remove them because we don't like them, or they just don't help us. We don't want to mess up our data by saying oh, this doesn't help us and goes against what we think, so we're just going to take it out. That's not how we work with data. But if somebody says I drink 10 days a week, we're that's not even possible, so we're going to remove them. We could go back and check the data, but a lot of times you remove outliers because the answer is just not even possible. So you remove outliers when you have good reason, and the good reason is the data just is not real. So there's sometimes a good reason to remove them. Very true. We don't remove them because we don't like them, though, not because they go against our hypotheses. What percent were neutral? Check out earlier. We did this. This is a marginal distribution. So the marginal distribution down below is 229 divided by 922, 992, whatever that is. So that is a 2308. Good answers, everybody in the chat. Okay, what percent of Marvel superheroes have the ability to fly? So we're going to look at Marvel superheroes only. Is this conditional or marginal? What do you think? What percent of Marvel superheroes? Is that conditional or marginal? I'm going to start showing you how to get it right here. Marvel superheroes. of Marvel superheroes have the ability to fly? Is that conditional or marginal? Careful. This is conditional. Good answers, though. Good practice. It's conditional because of only the Marvel superheroes. What percent have the ability to fly? So what's the math on this? So marginal is just on the outsides right here. Like that's a margin, that's a margin. So those are the margins of the table when you only consider one variable. So this is of the Marvel superheroes, what percent have the ability to fly? So only considering Marvel superheroes, what percent have the ability to fly? So that would be of the superheroes that can fly, what percent are Marvel? So if you do it this way, this would be of the superheroes who can fly, what percent are Marvel? So that's a different margin. That's a different conditional right there. That's setting the condition of the superheroes who can fly, what percent are Marvel? There we go. And good. Does that make more sense as we talk over the different ways to do this and the different ways it can be asked, like of the Marvel superheroes or given someone's a Marvel superhero of, or only considering Marvel superheroes? There's a lot of ways to say it, but you're narrowing it down to just these and then saying what percent of the ability to fly. So you're looking at one variable, setting a condition, and looking at the distribution of the other variable within it right here. So 115 out of 794. There it is right there. And good practice. Yep, that looks to be right. It's going to round to 3 decimals, so we're going to move this right here. There we go. Looks to be right there, Megan. Good work. Below is a contingency table. What's the probability of a student born in Tennessee being an honors student? We did this one earlier. Check out the longer walkthrough. Make sure you know how to do these. So we'd go right here and we'd say a student who's born in Tennessee being an honors student. So if you're born in Tennessee, that's setting a condition, and being an honors student, that's the within the other variable. So 50 out of 574. And there it is as a decimal right there. Boom. We'll do one more version of this. Let me know if you have more questions. We get that 10 out of 10. We did. Remember, it's all about understanding the concepts like conditional and marginal and what they mean. So make sure to take notes. We talked about this earlier where the outliers are at 1.5. Now, what else can we do with box plots besides the 1.5? Sometimes there's a what with box plots. What is going on right here? What's the deal with that point? What's the deal with that point right there? What's up with that point right there? It's a star. What's the deal with that star? Why do we have a star on it? Extreme outliers. Where are extreme outliers? Extreme outliers could be where? Extreme outliers are sometimes noted when they are what? Extreme outlier is where? So instead of the 1.5 limit, which is about there, extreme outliers, that's 1.5 IQRs. Well, so these are things outside the fence. That's outside the fence for that one. That's outside the fence. But why does this one get a star? Why does that one get a star? So the outliers that get stars, why do they get stars? It would have to be actually a little further up. It's going to be way up there probably. So why does it get a star? More than 3 IQRs above Q3. So if you went Q3 and went 3 IQRs above, so these are extreme outliers denoted by more than 3 IQRs above. So that's an extreme outlier right there. Now, which of these months has the greatest range? I do love this question. It is going to be one that catches a lot of people on the test. So once again, we're doing test review right here. Which of these months has the greatest range? So it should be very clear looking at this data, which month here, and we can compare multiple groups with box plots, which of these months has the greatest range? So which month has the greatest range? A particular month very clearly has the greatest range. A lot of people get this wrong. February, that is correct. Great job. Whenever you do the range, don't forget outliers. Is this the max? Is that point highlighted right there the maximum of December? Is that point highlighted right there the maximum of December? No. What is it? What is that point right there? What is that point? That thing I've highlighted right there is actually the what? I have a feeling what we said. Ah, do we see the fences? Do you ever see the fences in a finished box plot? Do you ever see the fences in a finished box plot? Do you ever see the fences in a finished box plot? No, we don't. Good answers, Megan, right there. That's why I asked it. So I want you, this is the review. This is the good stuff right here. Think about this right here. You ready? We have a data set right here. Let's just say data. And here's the data. Okay. Why is there no whisker on the top side of this? Why is there no whisker over here? Do you see the data? The highest value is 3. So let's add in 4 right here. Do you see how the whisker extended when I made it 4? Now there is a data point over here. But where is the fence? Where is the upper fence? Can anyone tell me where the upper fence is? This would be a really good test question, and let's show how to find it. Where is the upper fence? This would be a very good test question. Is that right? Close. So Skylar, good answer, Skylar. Good practice. That is not correct, but really good guess right there. A really good guess. So what's the answer to where the upper fence is mathematically? Like, what mathematics do we need to do? What math do we need to do to find the upper fence? And the notes are on the slides right here. What is the math we need to do to find the upper fence? The answer is right there. So to find the upper fence, Q3 plus 1, but careful. I think that's where the error occurred right there. It's 1.5 IQRs. Yeah, 75th percentile, Suna, you got it. And so we'll do that next. Cassandra, great work too. So think about this. Q3 is right here, and this is a really good question for Savannah right there. What does Q3 tell us? This is the what of the data. What does Q3 tell us? Q3 tells us what? What does Q3 tell us? That's the what right there. Because if it's 3/4, that's what does Q3 mean? And I've got the answer down there because Q3 is 3, ironically. So, well, Q3 means 75% of the data is below here. So 75% of the data is below here, so that's the 75th percentile. Does that make sense? So you can also find, and Savannah's got in the chat right there, this right here is the IQR. So what is the IQR? What is the IQR? Like mathematically, what is the IQR? Like just visually, and you can also solve it down here with the data down below. So you can solve it with the number line or the data down below right here, because that's Q1, that's Q3. So what is the IQR right here? Well, the IQR is going to be a distance. Good answer, Savannah, right there. But the IQR is going to be a distance. It's going to be 2. Good answers. Because does that make sense? This has a length of 2 right here. So the IQR can be Q3 minus Q1, which is 3 minus 1 for this data. You can see right here, Q1 equals 1, Q3 equals 3, and that is equal to 2. So if we're going to find where the upper fence is at, the upper fence is going to be where? We have to go to Q3 and do plus 1.5 IQRs. So where is the upper fence? Skylar, you got it. So what Skylar did right there is they plug in 3, and then they do plus 1.5 times 2, because remember we found 2 is the IQR down here. We said this is the IQR, which is the range of the middle 50%. So let's test our theory. Are you ready? If I change this to 6, Do you see how the whisker extends up to 6? But watch this. So the whisker still extends to 6, and then I do 6.2, and 6.2 is a what? 6.2 is a what right now? Only one word right there. You got to say 6.2 is a what? It's an outlier. But why does the data look like this now? And so look at the data up here. Why does it look, what's going on right here? Where's the fence? Well, remember, the fence is just a graphical technique. And if you look at the data up there, what's going on with the data? It's the 75th percentile. That is correct. So 75th percentile is where Q3 is at the top of the box. So what's going on with this right here? Look at the data. You can see the last few data points of 3, 3.5. Q3 minus Q1 is the IQR. So this is a big what in the data right here. See 3.5, 6.2. This is a big what in the data. You can see the data points up here. Those are the values, 3.5 and 6.2. A big gap in the data. So the fence, why don't we see the fence? The fence is right there, right? The whisker only goes up to the highest point that is not a what? The whisker only goes up, so it's only 1.5 IQRs. The whisker only goes up to the highest point that is not a what? And watch this. You see this right here? The whisker only goes up to the highest point. Is that making sense, Cassandra? Because Cassidy right there. Sorry, Cassie. I think I've called you Cassandra a few times. My apologies. Let me throw you some points. I want to get everyone's names correct. Does it make sense to see this visually, that the whisker is only going up to the highest point that is not an outlier? So you could have the instance where we have like 7 right there, and take a look at the data now. Now there's just 2 outliers. So let's mark this box plot, and I want you to tell me what one of these values is equal to. You ready? So let's go right here and be very careful and mark the box plot. This is good practice to make sure you understand what a box plot is showing you. I'm going to put numbers here, and I want you to tell me what all of these numbers mean. Okay, so number what is what? Like I've got 6 numbers on here. So tell me any of these values on a box plot, and then let's talk about them. 1 is the min. Boom. There you go. That's the minimum value. Q1. Yup. That's the bottom of the box. Median. And then Q3. Boom, right there. Now 5's a weird one. 5 is not the max, though. Got to throw some points for that. 5 is not the max. 5 is the highest point that is not an outlier. Highest non-outlier. Not the maximum, though. 5 is the highest non-outlier. Well, where's the fence? This is the good thing we keep bringing up. Where is the fence? Remember the deal with the fence? A lot of people say, well, where's the fence? We know exactly where the fence is. Remember, we found the fence. No worries. This is good practice. This is the max. Where's the fence, though? Well, the fence is Q3 plus 1.5 IQRs, which we solved out a moment ago, is 3 plus... I'm going off the screen right here. I got to raise it up a little bit. We have to calculate it exactly. And then in your final product, what? So the fence is at 6. The fence is at 6. So in your final product, what happens? When you make your box plots, especially with graphical software, in the final product, what happens here? In the final product, what happens? I'm showing right here. Here's the final box plot. There's you figuring out it. In the final product, you don't see the fences. You don't see the fences. You don't see the fences. So think about this. The maximum length of the whisker is that it could do what? The maximum length of the whisker is that what? The maximum length of the whisker is that it what? Look at that. the maximum length of the whisker is that it could do what? It could go right up to the fence. So does that make sense? Like, this is the whisker going up to 6. This is a data point at 6.01, which is just beyond the fence. 6 is on the fence, which is in the fence technically. But think about this. Why does the data look like this now? Because there is a large what from 3.2 to 6.01. There's a large what right here from 3.2, which is where that is, the highest point that's not an outlier. It's a large gap. But what happens if I change this to 6.6 right there? Do you see how that's not an outlier? So you don't see the gap in the data anymore because you're seeing the data go all the way up. So that's a big review of box plots right there. That is like the most you can understand them. Like, what would you say if I gave you test scores right here? So imagine I give you test scores and I make it a box plot. And, or you know what we could do? Watch this. Random normal with a mean of 80, standard deviation of 7, and do 100. And now let's go box plot. Okay. Oof, oof. Oh, I did. Wait. It's random normal. Oh, 80 observations. Okay. 100 observations, mean of 80, standard deviation of 7. Okay, there we go. Now, let me try to make it a little bit easier to see where that value's at. Sure. How would you interpret this value right here? And we could put a number on it, but what would this mean as a value right here? If this traces down to like 84.5, what would that mean? So what does this 84.5 mean? What does that value mean? On the box plot, what is the idea of that value? I will see. I can do a stem and leaf here in a second, Nick. You got it? What is that? If 84.5 is right here, what does that value mean? We're just tracing it down. What does that tell us? And so, Savannah, this kind of goes to your question right here. And so what's the 75th percentile mean? And Megan, great job right there. What does the 75th percentile mean? If I say that's the 75th percentile, and these are students' test scores, that would mean 75% of students what or what? It's Q3. It is where Q3 is at. That is Q3. And so what does Q3 mean, though? What does Q3 mean? These are all right answers. And keep it up. So what does that tell us? That it's Q3. It'd mean 75% of students on this test did what? 75% of students on the test. Exactly, Cassidy. 75% of students scored at or below an 84.5. So that is what the 75th percentile tells us. And this would be part of the 5-number summary with the min, the Q1, the median, the Q3, and the max. There are no outliers in this data set. That's why we don't see any extreme values with the outliers. But right here, we can see, we can also estimate the IQR is something about 9-ish, that distance. Chapter 5, number 6, Maya's asking for a different thing, whatever. Yeah, we'll do that one again here. It's a really good question. And then you can tell me how yours looks, Cassidy, and we will solve according to that. So we'll finish this off, but that was a big review of box plots right there and understanding more in depth what they mean. They show the same, very true. Take a look at the note where we show this a lot. Got to have that same common horizontal axis. Probability of student being born in Tennessee being an honor student. Born in Tennessee, honor student. Should be that right there. And round to decimals. I think that's right. Marvel superhero fly. So of the Marvel superheroes, which one can fly? There we go. And born in Tennessee probability. So born in Tennessee. And there it is right there. Submit quiz. We should have it. Yay. Okay. Good answers. So let's go back here. Let's do another version. Okay, so we're gonna do some more chapter 5, question 5 on the homework. We could do the whole homework. Well, if you're here, you get to ask the questions. So remember in the future, if you are in the future right now watching this and your question was not asked, just remember, swing by and we'll work on your question, especially if I'm on a rant. You can just go, hey, Brian, let's talk about this. Using the 60 and 80, what are the Z-scores on those, Cassidy? So what are the Z-scores on those? Like, give me the Z-scores of 60 and 80. Is it -3 and -1? Might be, or that might be -1, -2. It might have been 100 with, I'm guessing, is yours normally distributed with a mean of 100 and a standard deviation of 20? Is that the way your distribution looks? So it should be -1, -2, so 13.5. 0.5, 2.5, 2.35, 13.5. So let's show that right here. The answer should be 13.5. And we're going to show this. Oh my gosh, my hair. I might get a cut this week. It's going crazy. Crazy, crazy, crazy hair. Where is the empirical raw I like? Here we go. I got the picture of it. Okay, copy picture. Let's go grab this. And let's show it. Okay. Here we go. Yeah, Scholar, which one do you want to do? Name a question and we can do it. You got it. Okay, so we're going to do like a speed run of this question now. And we're going to show how to get some answers right here and show the normal model, speed running normal curve, let's call this. Or, I don't know, we want people to view this. So let's give it the same name. Speed run. Let me know which questions. Pick the question and tell me the start of it. And we can do that question. Looks like Count wants to too. So this is the curve, but what numbers do you usually know on the normal curve? What numbers do you usually know, like 68? So you should know those numbers. What numbers do you usually know on the normal curve? And if you want, take a picture of this graphic on the screen and save it. What numbers do you usually know on the normal curve? I think Cassidy's got them posted up above: 68, 95, 99.7. So guess what? These numbers can be obtained because, remember the 68 where we cut it in half? So if you cut 68% in half, you'll get that. But watch this. If 68% is inside of here and 95% is inside of here, then wouldn't, I'm double checking my mathematics, 27%, so follow my logic, because now we're just asking about these areas right here, wouldn't those be 27% total? Does that make sense, Cassidy, right there? 27% would be the area within both those combined. So how are we getting 13.5? We're dividing by 2. So that is half of that right there, because 27% is the difference between those up there. And then you do the same sort of trick with the next one, because if you have 95 within here, that's the 95% within plus or minus 2, and 99.7% within here. So what is total within here, Cassidy? So what are the total amounts? So you're doing perfectly, following along. Great job, Cassidy. What is the total within the yellow areas right there? Total, not what it says. But think about, we're just going to take the difference of those numbers. So what's the total outside, like, contained amounts? What's the total in that region? Because it's 99.7 minus 95. No worries, Cassie. Let me answer the question. That's great to say right there. It's 4.7. And if you divide it by 2, you get both of those regions right there. Thank you for saying that, Cassidy. I can definitely answer more. Thank you so much. All the participation done. Let me throw 100 points for all that participation while at work. Whatever you need to do at work, do that first, and then I'll answer more questions for you. So good answers right there. So all these numbers are obtainable via the 68, 95, 99.7. So we need to know that we can find these numbers. The 0.15 is just the outside of the 99.7, because outside of this you have 0.3 and cut 0.3 in half. 0.3 cut in half are these numbers right here. So what we can do with this graphic right here, which we should know how to get these numbers because they're all obtainable, we can go and put our numbers from the assignment where it says a mean of 100 and a standard deviation of 19. So we would go right here and we would put the mean of 100 and start going up by 19, start going down by 19. So now we've got the numbers below the curve, and we've got the the z-scores over here with like 0, 1, 2, 3 standard deviations, -1, -2, -3. So going back, we should see the same numbers with 100 at the center. There's 168 right there. And with this, it says the central 99.7, that's 3 standard deviations. So we can use the numbers they show us right here, 43 to 157. And now we go to the next one. It says above 157. Well, that's the very top of the curve, which was point, if you remember right over here, we have the above this is 0.15. And then going to the next one, we have 81 to 100. That's half of 68 right there. So that's 34. And then we have above 119, which is above here, which this is 68. So 32 on the outside, half of 32 is 16. And you could also add up the numbers below it. That's a really good question. The last one was asking above 119, which is above right here. And so you could add up these numbers, and adding up those numbers gives you the answer right there. Lots of ways to get this, like going 68 on the inside, and that leaves 32 on the outside. Half of 32 is 16%. Double check your work by adding them up to make sure they equal 100. Skylar, which question were you wondering about on chapter 4? I'm going to go take a real quick. I'll be right back. Chapter 4, yes. Here we'll be right back, and we'll start that one up. Okay, Skylar, let's go check out your question right here. Let's see. Is it the load times? A study reports load factors. Okay, chapter 4 quiz. Is it the what? Okay, let's go check out the load factors. Oh, points. Get those points. For quiz, replace question. If you see it, let me know. Here we go. Study reports load factors. Let's check it out. A stem and leaf? Yeah, here, let's do that next. Stem and leaf. In a way, box plots are the opposite. Here, let me grab that. In a way, I think I saw that one as we were doing this. And then stem and leaves. Example of a stem and leaf. You got it, Nick, right there. Okay, here we go. So on this one right here, a study reports the load factors. And yeah, so this is a box plot of the data. And then these are the years 2002, 2003, 2004, and so on and so on. And we have the percent load factors right here. And this is breaking it apart. This one is a weird one. I don't like the way they ask it. So this is a tougher one just by the way they're asking it. So I got to be worried right here. Outliers are context dependent. That is very true right there. If you notice within 2015, this is an outlier, but within the full data set, there's a lot of outliers. So that's very true right there. Data values that seem ordinary when placed against the entire data set, may we're going for this one. Data that values that seem ordinary when placed against 1 year data may stand out when compared against the entire data set. I think that's what it's going for. Outliers are context dependent. Data values that seem ordinary when placed against 1 year's data may stand out when compared against another year. Well, what they're going for right here is they're showing you that each of these box plots is made differently, because when you go within this year, there is very little variation. There's not even any whiskers on this. And this one has a tighter IQR. So that point, which would not be an outlier in many of them, is an outlier over here. But when you go to all the data together, so this is just taking all these box plots and putting them together, you can see there's a bunch more outliers. So I think we have this right here. Let me read it over again. Outliers are context dependent. Data values that seem ordinary when placed against 1 year's data may stand out when compared against the entire data set. That should be right. Woo! It's just very complex. It's a very complex question. It's almost like an essay question where I'd ask people to explain why do we not see as many outliers. So it's true they're context dependent. Like when you look at within each year, you don't really see any outliers. But then when you put the data as a whole, you'd get a new Q3, new Q1, which would calculate new fences. So the calculation of what is an outlier is really going to depend on the data, which is context dependent then. So it's much better as an essay question or something. That's a very, very complex question. Then Savannah asked in a way box plots. I think that was like number 4. I saw it back here. In a way. Box plots. Here we go. We see the box plot and histogram. Histograms are going to be much better at showing you the what. As I take the note right here on the question we're doing, histograms are a much better way to display what for us. What are histograms going to display a lot better than box plots for us? Histograms are a lot better at displaying the what of a distribution. So histograms, just one word, histograms are going to let you see the what a lot easier. Take a screenshot here and I'll start drawing it. Histograms are a quantitative display of data, univariate. They display just one variable like number of streets, and they're going to give you a much better view well, of the shape. We can see that this is a monster man, and good answers, Nick, right there. This is a right skew monster man. So we got the outliers, we got the skew, we got the gap. So we got a good idea of the shape right here. Now, what does the box plot tell us really quickly? What is the box plot going to give us very quickly right here? The box plot is going to give us these things right here. Yeah, well, skew is a part of shape. Good idea right there. So what does the box plot give us very quickly? The box plot will always tell us the what, which is very important too, which the histogram won't give us. So there are 2 ways of displaying the same data. Well, you can see outliers too in both of them. So both of them give outliers. But box plots very specifically are going to give you these values right here. So both of them can let you see where outliers are, but box plots are going to have the advantage of really showing the what right there. And I've highlighted down below. Where histograms are going to show you shape a lot better, box plots are going to show you what? The 5-number summary. Yes. So you've got the 5-number summary down here, 5-num sum. So the box plots are going to give you a better view of the 5-number summary, where the histogram is going to give you a better idea of the shape. So kind of some big reasons to use different ones. And then why would somebody have a stem and leaf? So what is a stem and leaf going to show you? If we go over here and go to stem, what does a stem and leaf show you of the data? So like, what does that value right there mean? What do those mean? So what does the stem and leaf show you? So these are test scores of students, and you can't even see the data, but this is a stem and leaf right here. What can you tell from the stem and leaf? Here's the box plot of the data. I could show you the histogram of the data over there on the side. So what? The box plot shows us the 5-number summary. There's the histogram. So what was the lowest score on this test? What was the lowest score and the highest score on the test? And this will answer the question. And people were wondering about stem and leaves also. What was the lowest and highest score on this test? What were the lowest and highest scores on this test? So use the information available to you right now to find the lowest and the highest score on the test. Ah, Nick, but be careful. 65 to 70 is a bin of data. And Andrew has it right there. Great job, Andrew. Or double check, Andrew, on the last one right there. Yes, exactly, Andrew. Great work. So there's data points between 65 to 70. This just means there's an observation right here. So there are observations between here, and you can use the count on the left side to see there's about 2, and it's the 68 and the 69 right there. So the stem and leaf lets you see what? So if we were to look at the test score data and sort it, you can actually see, well, we should round it. Let me round it to 1 decimal. Round it to 0 decimals so we don't get crazy stuff like that. Round test score. Go right here. There we go. So the lowest grade was a 68, and let's look at the stem and leaf again. So the lowest grade was a 68, and the second lowest was a 69, and there's the values there, and that's the 2 values in that bin, where the highest grades on the test were a 95 and 96, and the 95 goes in this bin to the right because it's right there. Is this making more sense? Like, here are the grades. You can see the grades in this bin if you highlight these values right here, and these would be the grades right here. You can also see a lot of grades between 75 to 80. It doesn't include 80, it goes up to. So all these grades right here are why this bin is so high. Sugar is a major ingredient. You guys, Sydney, yep. And so if you notice, the histogram gives you a better idea of the right skew. It's got a little bit of right skew. The stem and leaf lets you see the actual numbers, where the box plot is going to show you the 5-number summary. These are all the same displays of data that we're seeing on the screen, because histograms, box plots, stem and leaves are all the same display of data. A dot plot, which I'm not a fan of, you could just literally take the stem and leaf and just turn it into dots. You could just make those dots, and that'd be a dot plot. I'm not a huge fan of those. I'd use another graphical display. So let's look at what the question asks. Explain how you could tell. Explain how you could tell by looking at the box plot where the tallest bar would be. This is a really great question. Which area on this box plot has more data? Yes, Andrew, exactly. I think it showed it on that. Oops, I did my rainbow. I think it does show it, but you need the legend. So which area has more data? Are you ready? This area right here, area 1. Which area has more data in it? Or area 2? Area 1 or area 2 has more values in it. Like if I were to highlight that data and this data, which one has more? So to answer this question, if you're wondering how to answer it, because this is the key, what they're getting out with this question, is we need to mark that starts at Q1 and goes up to the median. And this one starts at Q3 and goes to the max. What percent of data would there be between Q1 and the median? What percent of data would be between Q1 and the median? Think about the percentiles. What percent of data would be between Q1 and the median? So what percent of data is between Q1 and the median? Not 1. So Q1 is the what percentile? Good answer, Savannah, right there. Q1 is the what percentile? Q1 is the what percentile? 25th percentile, right? So we're asking between the 25th and the 50th percentile, what percent of data is there? How much data is contained between the 25th to the 50th percentile? How much data is there in this region? There's what percent of the data? Like what percent of all the data is there? That's what percent of the data from this graphic? 25%, right? Because, well, 25%, exactly. So the other one I asked about was over here on the right side. And if you notice right here, this goes from Q3 to the max. So what percent of data is over there? What percent of data is there over there? from Q3 to the max, which is the 75th percentile, to the 100th percentile, what percent of data is there? 25% again. So how could we tell where more data is? By how compact these lines are. So do you see this is the min, and the min to Q1 is the most compact region. Does that make sense? I didn't mean to click that. The min to Q1 is the most compact region of the data. So how close the numbers in the 5-number summary are, let us know that the peak in the histogram, which is right here, is going to be in this compact area of data, because this is where the min, I meant to write min right there, that's where the min through Q1 is. Now, what percent of data did I highlight right there? What percent of data have I highlighted from the min to Q1? From the min to Q1 is what percent of data? 25%, exactly. Because it breaks it apart. You can literally see between all of these is 25%. So there's 25% here, 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 and here. The most spread out is the top 25%. Okay, so the answer is going to be the tallest bars, no. The area in the box plots where the two vertical lines are closest together contain the tallest bars. There's the vertical lines right there, vertical line there, vertical line there. It should be careful because that's not a number in the 5-number summary. Okay, really good question. Like the theory behind understanding it's the main important part. If I just show an answer, I like to explain it. Explain how the box plot and histogram can indicate skewed direction. So the skew will be the way it's pulled out. When you see separation between the 5-number summary, you're going to see more skew. So you can tell this is right skew because you're starting to see Q3 and the max are further away. So Q3 and the maximum value, my handwriting is really bad today. Q3, which is right here, and the maximum are much further away than the min and Q1. So the histogram very clearly shows it by just the shape. So box plot indicate a skewed direction because the minimum, first quarter, and median occur with a smaller range. So we're going to go for that. The box plots indicate a skewed direction because the min, first quarter, and median occur over a smaller range, min, Q1, median, where the spans between the median, third quartile, and maximum, median, third quartile, and maximum are much larger. The histogram indicates a skewed direction since the taller bars are on the left side. Yes, that's right there. Identify one feature of the distribution that the histogram shows, but the box plot does not. The histogram is going to show shape a lot better. The histogram shows the presence of outliers. No, they both do. The histogram shows the location of the median. No, that is a box plot. So let's go down here. Box plots are going to show the median. Hey, Jesse, good to see you here. And the histogram shows that the distribution is roughly uniform. Uniform means flat. Let's just draw that really quick right here for people to see if we hear uniform, which this is not. Uniform is one form. Unimodal is one mode. This is unimodal, not uniform. Very important to know the difference. The histogram, no, wait. The histogram shows that the distribution, no. The histogram shows that a very large number of values occur in a small bin. I mean, that's kind of right. Let me look at the other ones. This histogram shows the center of the median impossible. It's not uniform. This histogram shows the presence of outliers. No, they both show outliers, so it has to be that. There we go. This histogram shows a very large number of values occur. Well, we could kind of assume that, which they had us assume. It's much easier to see that with the histogram. It should say it's easier to see. The other answers are just wrong. Like the histogram and box plot show outliers. The histogram shows the location of the median. That's the box plot. The histogram shows the distribution is uniform. No, it's not uniform, so that has to be wrong. So sometimes, whoops, bump my mic up. Sometimes you can do a process of elimination because no, box plots show medians. Histograms are better at showing shape. So did that say, yeah, I mean, it should just say it's better at showing shape, which is the key thing. You can really, you can see the peak a little bit better. Or they should say the histogram just shows shape better. Other questions? We did a stem and leaf. Should we do another stem and leaf? We don't have any other questions on the docket. You're welcome, Nick, right there. And we did some stem and leaves. What other questions should we do? We are free right now to do questions. It's freebie question time. Fourth graders? Oh, this is a good one. This is a tricky one. This one gets a lot of people. A class of fourth graders. Cereal one? Oh, cereal. Thank you. How's the cereal one start? Sugar. Yeah, thank you, Sydney. Sugar's a major ingredient. I found the children one already. I know the sugar is a major ingredient. 100 points. Catching a question Brian forgot. Thank you so much. That one slipped through right there. I got sugar's major ingredient and a class of 4th graders. Do remember the goal is to learn how to do these. So ask any questions you got. Thank you so much, Andrew, once again. So this is a tough one, surprisingly. So what are they showing to us for these kids? Why do we have 5 numbers on the board? What are they showing us about these kids? And then let's make sure we understand like what these values mean. So we got boys and girls, and we've got the what for these kids right here. Someone's reported to you the what for these kids. Well, it's a reading test, and it's a 5-number summary, right? Great job, Sydney and Andrew right there. It's a 5-number summary. So this means for the 12 boys, what? That's Q3. For the 12 boys, what? For the 12 boys, what? For the 12 boys, what? What does Q3 mean? Take a guess at it and then just understand what Q3 means. Like we'll practice understanding what does Q3 mean? For the 12 boys, what? It might work if we go look at our data because we have actual data with test scores. If we go and get the 5-number summary for this, so let's go here and do quantiles. On this test, 75% of people made at or below an 84. Does that make sense? So if you go to this test over here, there's the 5-number summary, and you look at this, and you go to 84, this is 75% of people. So 75% made at or below an 84 because that's where Q3 is at. It also means 25% made above this. So you could talk about the 75th percentile being where the top 25% of the class is. So the top 25% of the class made at or above an 84, and that's where Q3 is at. And you're going to see this a lot better if you do something like a box plot right here where you can see 84 is where the 75th percentile is at. So 75% of people made at or below an 84 because that's where Q3 is at. So we're getting the same sort of information over here where it's reporting to us Q3. And unfortunately, I drew on this, so I have to redo my drawing right here to make sure I've got this labeled properly with the min, the lowest grade in the class, Q1, the bottom 25%, the median, where the 50th percentile is at, the Q3, where the top 25 starts, or the bottom 75 would be below that, at or below, and then the max right there. Once again, know what these values mean when we talk about the 5-number summary and how it relates to the percentile and where you would be in this distribution over here. Like the minimum is at the very bottom right down here. I know that says 65, but that's a value between 65 up to, but not including 70. The maximum, which is 96. Once again, the bins on the histogram are 5 here, so it's a value between here, which the highest value is 96. So we know what the 5-number summary is, and we can solve this problem. Which group had the highest score? Well, it's just asking the max, and that is the boys right there. So the boys right there had the highest score of a 5.9. Which group had the greatest range? Well, that's max minus min, and we can do it right here. That's 3.5 for the girls, and you just need to solve both ranges. So girls are going to be 5.6 minus 2.1. There's the range. And the guys are 3.4 because it's 5.9 minus 2.5. The range, once again, is max minus min. So just take the difference respective to the group, and you will find the proper value. Next, we get which group had the greatest interquartile range. It's kind of neat that they do this next right here because the interquartile range is just the range of the middle 50%. And it's going to be the boys right here with a range of 1.0 because the girls have a range of 0.9. And so we go right here and we do 5.1 minus 4.1. And there's the boys' IQ right there and the girls is 0.9. So find both, double check, and the boys right there is 1. Which group did better? Well, girls had a higher median. I think that's just it right there. The girls had a higher median. Doesn't mention anything else. Now, this is the tough part. Now, this is where they're trying to trick you. There are 12 boys and 4.6, or 12 boys and 11 girls. So it's actually going to round up right here. I think I got the easier version of the problem because it does round up, but you have to solve it this way. Let's go ahead and take the work right here and solve it. Okay. So you have to take the boys' average, which was 4.7, times it by the amount of boys, add that to 4.6, times that by the amount of girls, and divide by the total. So this down below is the total for the boys and the girls, how many students there are, and 4.7 and 4.6 are the averages respective. This is making a weighted average. Now, it's going to round up to 4.7, but it doesn't always work that way. You don't always get that. This is the tricky part. You have to do the boys' amount times the boys' average, girls' amount times the girls' average, and then right here, the total right there. So 4.7 times 12, and now 4.6 times 11, but we get an error. There we go, and that does round up to 4.7. It doesn't always work this way. This is a very commonly missed question. So 4.7 right there, very commonly missed question. That question down there, it does not always round up. A lot of people just put in like, okay, it rounds up, but it's a weighted average. And so you have to put in the boys amount times the girls amount. Once again, showing the work over here on how to get it. We have the boys average times the amount of boys, girls average times the amount of girls, divided by the total. 12 plus 11 is 23. And that gives it a weighted average right there. So you have to use the values given in the problem. Good question. I think we got the cereal question next. Cereal is a major ingredient. Cereal. Sugar is a major ingredient. Oh, we didn't take the timestamp on the fourth graders. Okay. Sugar is a major ingredient. Okay, let's take a look at it right here. And here we go. What is the range of these sugar contents? So who can tell us in the chat, what is the range of these data values? Who knows what the range is? This is a good question to practice and review, because a lot of times people look at this data very quickly and they see what's going on, but they look at the histogram. So who knows the range of the sugar content here? So the range is always the max minus the min. The range is always the max minus the min. So what is the range? Great answers. It looks to yours might be 65. This one goes from 1 to 65 right here. So it's going to be 65 minus 1. So 65 minus 1 is max minus min. And that is the range right there, which is 64% from max minus min. The bins in the histogram don't always show you the lowest or highest value. And that's got it right there. The shape of the distribution is very much bimodal due to the adults having low sugar and children having high sugar. One aspect is very clear. Cereals tend to be either. That looks good right there. And sugar values vary greatly. That would just be a high standard deviation. Similar is going to be uniform. Are adults' children always low? Are children's cereals always higher than adults? And so we would want to look at the max for adults and the min for children. The answer is yes. So looking at the max for adults and the min for children, very much so. Now, when we talk about the variation in sugar content, we could look at the IQRs or the spread of it, the range of it, excuse me. So comparing two different metrics right here of spread to see which one's more spread out, the IQR for the children's cereal is going to be right here, and the IQR for the adult cereal is right here. So adults clearly have a bigger IQR, which is a measure of variation. But the range for both is very similar. So we have similar ranges, but very different IQRs. The adults have a much larger range to the middle 50% of their data. So that's got that. So although the ranges appear to be similar for both groups, the IQR is larger for the adult cereal, and that should do it right there. Good question. Once again, understanding what the box plots are showing you is key. Check out the section of the video where we did a really deep dive on box plots. What other questions are there? We'll see if we got one or two more. I might need to grab some lunch here. Do a question, maybe more. Who has questions? Might grab some lunch. Got class coming up here soon. Class coming up soon. We did some review of box plots today. We did the canvas content. I think it might be time for lunch. With that, everyone, probably going to save what we did. We did a good bit of work. We'll be back here. I'm going to send out the announcements for class. Until then, bye for now. I'll see you next office hours. Bye.